Good evening, everyone. I'm Joel Moore, the interim chair of the Berkeley Physics Department, and it is my great pleasure to welcome you this evening to the annual J. Robert Oppenheimer Lecture. Since 1998, Berkeley Physics has had the opportunity to bring truly world-renowned theoretical physicists to campus to speak in honor of J. Robert Oppenheimer and his legacy. This lecture series occurs every spring, and it highlights trends, discoveries, and groundbreaking research in theoretical physics, and it was made possible through the generosity of Jane and Robert Wilson. Before introducing tonight's lecture, I would like to say a little bit about the Berkeley Physics Department and some news, and say a little bit more about Oppenheimer and his legacy and what he particularly means in the present time. To start with, Oppenheimer was a theoretical physicist and created the first school of theoretical physics in the US at Berkeley. He came to Berkeley 1 year after Ernest Lawrence, who was maybe the largest figure in Berkeley's experimental physics program. And between them, they turned Berkeley into one of the best departments to do physics in the world. Oppenheimer's achievements in physics, I would normally tell you a lot about. These include the Born-Oppenheimer approximation for molecular wave functions and work on the theory of electrons and positrons, the Oppenheimer-Phillips process in fusion, and various other things. I would like to focus tonight on another aspect of Oppenheimer's career, which is what he did after he was at Berkeley. You may have heard that he was the scientific leader of the Manhattan Project, the project to create the atomic bomb. And in that capacity, he was an incredible scientific manager. And normally, management is not the most exciting thing to talk about. The particular point I would make is that Oppenheimer put together an unbelievable collection of talent. And this is not so much a scientific thing to me as it is being able to recognize very smart people and get them together and then get out of the way, I think is Oppenheimer's great achievement. And one point I would like to make about that talent is some of it was born in the US, like Richard Feynman, for example, but a great deal of it was not. Much of it was immigrant, and of that part, much of that was refugee. And I think a great deal of America's leadership in post-war physics came from that Manhattan Project generation. And that's why if you try to talk with physicists about politics, you'll get widely different opinions. Even with Oppenheimer, you will get different opinions on, was Oppenheimer sufficiently careful about security? Was the atomic bomb a worthwhile exercise? And so on. Physicists are very capable of disagreeing. You will very rarely hear a physicist say, in fact, never in my experience, that American physicists have not benefited greatly from international collaboration and from people coming from other countries. And I think that's probably worth remembering. So Oppenheimer's progress as the founding father of the American School of Theoretical Physics was to ask what a talk was about, or what a piece of physics was about, what was learned by it, and what were the remaining unsolved problems. And we continue to ask those same questions, and that's the theme of tonight's lecture. So as I mentioned, the Oppenheimer lecture we've had since 1998, and it's become a very nice tradition in our physics department, and there are new things happening that I believe will last at least as well and become new traditions, and I wanted to call your attention to a couple of those. One is, tonight is a night for theory, but we have created a new experimental program at the undergraduate level, Physics 5, with a beautiful new laboratory that I think is going to make Berkeley, if it isn't already, the best place to learn experimental physics as an undergraduate in the world. We have a new Center for Quantum Coherent Science, which is actually very connected to the kind of work that you'll hear about tonight. It's very much in the same theme that certain fundamental ideas of quantum mechanics unify a vast number of different areas of physics. So that's one of our main priorities in research at the moment. And then lastly, in order to link physics with the outside world in the same way that Oppenheimer did, we have a new industrial partnership program called Berkeley Physics Partners, or BP2. And I would be happy to talk with you about any of these things, but I think with that, let me move on to a little bit more about science and the Oppenheimer lecture and our distinguished guest tonight, Professor Preskill. So Oppenheimer lectures since 1998 have included 6 Nobel laureates and distinguished figures from all areas of theoretical physics, ranging from astrophysics to condensed matter to cosmology to atomic and molecular physics. Tonight, we have an unusually broad speaker in that Professor Preskill's lecture on quantum computing and the entanglement frontier will take us on a journey into quantum entanglement and the various aspects of physics that it unifies. So Professor Preskill comes to us from the California Institute of Technology, better known as CalTech. He is the Richard P. Feynman Professor of Theoretical Physics there, and he's also director of the Institute for Quantum Information and Matter at CalTech. And that institute, which has existed for quite some time now, I believe it started in 2000, was one of the first to recognize that notions of quantum information are very powerful in linking the work of physicists in different disciplines. Getting back to Professor Preskill, he received his PhD in physics in 1980 from Harvard and moved rather quickly to CalTech in 1983. He is a member of the National Academy. He is a two-time recipient of the Associated Students of CalTech Teaching Award. He's mentored more than 50 PhD students and more than 45 postdoctoral scholars at CalTech, and many of those, a few of those are here, I believe, and many of those have gone on to be leaders in their research areas. So if I had to pick a few sentences to sort of summarize the theme of his research, at least since 2000 or so, he's especially intrigued by the ways that our deepening understanding of quantum information and quantum computing can be applied to other fundamental issues in physics, such as the quantum structure of space and time. Aside from his research papers, his celebrated lecture notes from his CalTech course on quantum computation, which by this time includes a great deal of things that I wouldn't necessarily call computation, they've exerted a profound influence on the development of the subject. And I would say that CalTech has become one of the leading centers for theoretical research on quantum information and quantum computing. Our own Center for Quantum Coherent Science has a different emphasis in some ways. It's based on what Berkeley leads in. But it's fair to say that one of our intellectual progenitors in setting up this new center was what's been done at CalTech. So Preskill has been described as less weird than a quantum computer and easier to understand. I agree with the second part, and the first I'll reserve judgment until after the talk, but we are thrilled to add Oppenheimer Lecture to his very long list of accolades. Please join me in welcoming Professor John Preskill.
Thank you very much, Joel, for the beautiful introduction, and I'm deeply honored to be here to carry on the tradition of the Oppenheimer Lecture and to join the roster of great scientists who have preceded me here. I'm going to be talking about quantum physics, but also about information. Everybody knows that information technology has had a huge impact on our everyday lives, but we also recognize that information technology that seems impressive to us today is going to be surpassed in the future by new technology that we can't really expect to imagine today. It's interesting just the same to speculate about future technologies, and I may not be the ideal person to engage in that type of speculation. I'm not an engineer, I'm a theoretical physicist, and I can't really claim to be deeply knowledgeable about how computers really work. But as a physicist, I do know that the crowning intellectual achievement of the 20th century was the development of quantum theory, and it's natural for a physicist to wonder how the development of quantum theory in the 20th century will impact 21st century technology. Quantum theory is, of course, an old subject by now, but some of the deep ways in which quantum systems are different from classical systems, we've only come to appreciate relatively recently. And a lot of those differences have to do with the properties of information encoded in physical systems. To a physicist, information is something we can encode and store in the state of a physical system, like, for example, the pages of a book. But fundamentally, all physical systems are really quantum systems governed by quantum mechanics. And so information is something that we can encode and store in a quantum state. And physicists have appreciated for a long time that information carried by quantum systems has some notoriously counterintuitive properties. That's why we like to speak about the weirdness of quantum theory. And we relish that weirdness and find great enjoyment in it. But we're also starting to ask more seriously in recent years whether it's possible to put the weirdness to work to exploit the unusual properties of quantum information to perform tasks that wouldn't be possible if this were a less weird classical world. And that desire to put weirdness to work has driven the emergence of a field we call quantum information science, which derives much of its intellectual vitality from three central ideas, which are quantum entanglement, quantum computing, and quantum error correction. And my goal in the talk is to introduce you to these ideas. I'd like to start at the beginning. We all know that any amount of digital classical information can be expressed in terms of indivisible units, bits of information. And we might think of a bit as a physical object like a ball, which can be either one of two colors. Now, if I want to, I can store a bit inside a box, and then later on, if I want to recover the bit, I can open the box and the color that I put in comes out again, so I can read the bit accurately. And when I speak of quantum information, what I mean is information carried in a quantum system, and it too can be expressed in terms of indivisible units, what we call quantum bits or qubits for short. And for many purposes, it's useful or instructive to envision a qubit as an object stored inside a box, but we have the option of opening the box through two complementary doors, which correspond to two different ways in which we can prepare or observe the state of the qubit. And you can put information in door number 1 of the box or door number 2, and if later on you open that same door again, the color ball that you put in comes out again, just as though the information were classical. But if I put information into a qubit through door number 1, for example, and then later on I observe the qubit through door number 2, observe it in the complementary way, then no one can predict what we'll find. There's a 50% probability that the ball is red and 50% that it's green. So if you want to read quantum information, you have to do it the right way. If you do it the wrong way, then you will unavoidably damage the information. And one consequence of that we can appreciate if we think about copying a quantum state. If I had a quantum copy machine, that would mean that if I happen to have put information through door number 1 of a qubit, I can make a copy of the qubit, and then if I open the original and the copy through door number 1, then the color ball that I put in would come out of both boxes. And likewise, if I happen to have put information in door number 2 of the original qubit, once I built a copy, I could open door number 2 on the original and the duplicate, and the color that I put in would come out of both boxes. But in fact, no such quantum copy machine is possible. It's not allowed by the laws of physics. We can't make high-fidelity copies of unknown quantum states. And the reason why not is that in order to make the copy machine has to probe inside the box, and if it guesses right and uses the same door that I did, then it will be able to copy the information just as though it were classical. But if it guesses wrong and opens the wrong door, that will damage the information, and there won't be any way to build a high-fidelity copy. So although we might be able to clone a sheep, we can't clone a qubit. Now, I've described qubits in an abstract way, which I think is a useful way to think about them. But a qubit always has some physical realization, and I'll give a few other examples later. But just so you'll have something concrete to think about, we could consider, for example, the qubit to be a polarization state of a single particle of light, a photon. The photon has an electric field, and if it's oriented either horizontally or vertically, that corresponds to looking through door number 1 of the box. And if the polarization is tilted to the 45-degree rotated axis, that corresponds to door number 2. So, for example, we could make a horizontally polarized state of a single photon and observe it through the tilted axes, and what we would generate is just a random bit. But the really interesting ways in which quantum information is different from classical information, we can only appreciate if we consider states of more than one qubit. So let's imagine we have 2 qubits, and they could be far apart from one another. One at CalTech in Pasadena, the other in the custody of my friend in the Andromeda galaxy. And some time ago, these 2 qubits were both on Earth, and they interacted in a certain way that prepared a correlated state of the 2 qubits, which has some unusual properties. Namely, I can open my box in Pasadena through either door number 1 or door number 2, and either way, what I find is just a random color with the 50% probability of being either red or green. And the same thing is true for my friend in Andromeda. He can open the box through either door number 1 or door number 2 and just finds a random bit. So neither one of us finds any information in the boxes by opening a box in Pasadena or Andromeda, which seems kind of funny because with 2 boxes, we should have been able to store 2 bits of information. But where has that information been hidden? The answer in this case is that all the information is actually encoded in the correlations between what happens when you open the box in Pasadena and when you open it in Andromeda. Because it turns out for this particular correlated state of the 2 qubits, if I open door number 1, what I find might be red or green, but if my friend in Andromeda also opens door number 1 for that particular qubit pair, he's guaranteed to find the same color that I do. And the same thing is true if we both open door number 2. As long as we open the same door, we're guaranteed to find the same color. And there are 4 perfectly distinguishable ways in which a box in Pasadena could be correlated with a box in Andromeda. We could see either the same color or opposite colors when we both open door number 1 or both open door number 2. And by choosing one of those 4 ways, we've encoded 2 bits of information in our pair of qubits. But what's unusual in this case is that information is completely inaccessible locally. It's a property stored non-locally, shared by the 2 distantly separated qubits. And this property, that information can be shared non-locally between distantly separated objects, is what we call quantum entanglement. And it's the really important way in which quantum information is different from classical information. Correlations themselves are nothing unusual. We encounter them all the time in daily life. My socks are normally the same color. So if you look at my left foot and observe my sock, then you know without looking what color to expect when you look at my right foot. And it's kind of like that with the quantum boxes. If I want to know what my friend is going to see when he opens door number 1 in Andromeda, I can open door number 1 in Pasadena to find out. And if I want to know what he'll see when he opens door number 2 in Andromeda, then I can open door number 2 in Pasadena to find out. So it might seem to you that it's really the same thing, that the boxes are just like the soxes. But I claim that in fact they're fundamentally different. The boxes are not like the soxes. And the essence of the difference is there's just one way to look at a sock. But because we have these 2 complementary ways of observing the qubit, the correlations among qubits are richer and more interesting than the correlations among ordinary bits. This phenomenon of quantum entanglement is an old subject. It was first explicitly discussed in a paper by Einstein, Podolsky, and Rosen in 1935. And to Einstein, entanglement was so unsettling as to indicate that something's missing from our current understanding of the quantum description of nature. And that paper elicited some thoughtful responses, including a particularly interesting one from Schrödinger. The way Schrödinger put it was, the best possible knowledge of a whole does not necessarily indicate the best possible knowledge of its parts. What Schrödinger meant was that even if we have the most complete description that the laws of physics will allow of a pair of qubits, we're still powerless to predict what we'll find when we open door number 1 or door number 2 of one of those 2 qubits. And it was Schrödinger who suggested using the word entanglement to describe these unusual correlations. He also said it's rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. And what Schrödinger meant is it seems funny that it's up to me to decide by either opening door number 1 or door number 2 in Pasadena whether I'll know what my friend will find when he opens door number 1 or door number 2 in Andromeda. But Schrödinger understood that these correlations, though different from ordinary correlations, don't allow us to send an instantaneous message from Pasadena to Andromeda. When my friend in Andromeda opens his box, he just finds a random bit, and the probability distribution governing what he finds is not affected by what I choose to do in Pasadena. so no message is sent from one party to the other. Now, this theory of quantum entanglement really didn't advance very much for the next 30 years until the work of John Bell in the 1960s. And beginning with Bell, we started to think about entanglement in a rather different way, not just as something weird, unsettling, and surprising, but as something potentially useful, a resource that we can use to perform tasks that wouldn't otherwise be possible. We don't have to go into the details, but what Bell described can be thought of as a game that two players play. Alice and Bob, it's a cooperative game. Alice and Bob are on the same side. They're trying to help each other win. And the way the game works is that Alice and Bob receive inputs, and their task is to produce outputs which are correlated in a way that depends on the inputs that they both receive. But under the rules of the game, Alice and Bob are not allowed to communicate with one another between when they receive the inputs and when they produce their outputs. And for this particular version of the game, if Alice and Bob play the best possible strategy, they'll be able to win the game with a success probability of 75% if we average uniformly over the inputs that they could receive. But there's also a quantum version of this game where the rules are exactly the same, except that now Alice and Bob are allowed to use entangled pairs of qubits which have been distributed to them before the game began. And with those shared qubits, they can play a better quantum strategy which allows them to win the game with a higher success probability, about 85% rather than 75%. So they can use entanglement as a resource to perform a task, winning the game, better than they could using just classical correlations that they share. And experimental physicists have been playing this game for decades now and winning with the higher probability of success, which Bell pointed out the laws of quantum mechanics will allow. So it seems that the super strong correlations really are part of nature's design. Well, Einstein didn't like quantum entanglement. He called it spooky action at a distance. This sounds even more derisive when you say it in German. But it doesn't even matter what Einstein thinks. Nature is the way experiments reveal her to be, and we should all learn to love her as she is. So, boxes are not like socks is. Quantum correlations are different from classical ones. You can use them to win a game with an 85% success probability instead of a 75% success probability. Is that a really big deal? Yeah, it's really a big deal. And we can appreciate better why it's a big deal if we think about more complex systems with more qubits. We can think about quantum entanglement this way. Imagine a book. It's 100 pages long. If this were an ordinary book, written in bits, you could read the pages one at a time. And every time you read another page, you'll know another 1% of the content of the book. And after you've read all 100 pages, you know everything that's in the book. But suppose it's a quantum book written in qubits, and suppose the pages are highly entangled with one another. Then when you look at the pages one at a time, all you see is random gibberish, revealing almost no information that distinguishes one highly entangled book from another. And that's because the information in the quantum book is not written in the individual pages. It's stored almost entirely in the correlations among the pages. That's quantum entanglement. And these correlations can be very complex and are hard to describe in terms of classical bits. So for a modest number of qubits, just a few hundred, if I wanted to give a complete description in classical language of all the correlations among 300 qubits, I would have to write down more bits than the number of atoms in the visible universe. So it'll never be possible, even in principle, to write down that complete description of all the correlations. And that property of quantum information was very intriguing to the physicist Richard Feynman. It led him to make the suggestion in the early 1980s that if we could build a computer that operates on qubits instead of bits, a quantum computer, we'd be able to perform tasks that are beyond the reach of any conceivable digital computer. Feynman's idea was that if we can't even express in terms of ordinary bits the information content of a few hundred qubits, then by processing the qubits, we ought to be able to perform tasks that a digital computer would never be able to emulate. And at the time Feynman was making this suggestion in the early 1980s, there was an undergraduate at CalTech studying mathematics. Like all of our undergraduates, he studied quantum physics as part of our core curriculum. And like most of our undergraduates, he retained what he learned and later put it to good use when he made a remarkable discovery. Shor thought about the problem of finding the prime factors of a composite integer. This is a problem which we think is hard for classical computers, though there's no mathematical proof of that. And what Shor found is that if we had a quantum computer, the factoring problem would be easy. It wouldn't be much harder than multiplying two numbers together to find their product. And when I heard about this in 1994, when Shor made the discovery, I was really awestruck. Because what it means is that the difference between hard and easy problems, the difference between problems that we'll be able to solve someday with advanced technologies and the problems that we'll never be able to solve because they're just too hard, that boundary between hard and easy is different than it otherwise would be because this is a quantum world, not a classical world. And I thought that was one of the most interesting ideas I'd heard in my scientific life. And thinking about it eventually led me to change the direction of my own research from elementary particle physics to quantum computing. Now, does anybody care whether factoring is a hard problem? Yeah, in fact, a lot of people care, because the security of the protocols that we use every day to protect our privacy when we communicate over the internet are based on the presumed hardness of factoring and other similar number theoretic problems. And in a few decades, when everybody has a quantum computer, we won't be able to protect our privacy using these protocols. We'll have to do something else. Alternatives exist, but it's still not exactly clear what will be the best way to protect privacy in the coming post-quantum world. The important thing that we learn from Shor and others is that there's an interesting classification of problems, that there are problems that are hard classically and quantumly easy, can't be solved by ordinary digital computers, could be solved if we had quantum computers. And it becomes a compelling research question to understand better what are the problems which are of such intermediate difficulty. And we've learned a lot of things about that in the last 20 years, but I think the most important thing we know from a physicist's point of view about quantum computers is that we think, though we can't say this for sure, that with a quantum computer we'd be able to simulate efficiently any process that occurs in nature, which isn't the case with digital computers, which are unable to simulate highly entangled systems. And that means with a quantum computer we'd be able to explore physics in new ways. For example, by simulating strongly coupled field theories, we'd be able to compute the properties of complex molecules, study exotic quantum materials, and study fundamental processes like the formation and evaporation of a black hole, or the properties of the universe right after the Big Bang. So a lot of people work on developing applications for quantum computers, even though we don't have large-scale quantum computers yet. One of them is my friend Eddie Farhi, who, like me, is a lapsed particle physicist. And when he wrote one of his brilliant papers a few years ago, it inspired me to send him a poem, which read in part, "We're very sorry, Eddie Farhi, your algorithm's quantum. Can't run it on those mean machines until we've actually got them." And the poem goes on, but the point is that we have a lot of interesting ideas about what to do with quantum computers, but we don't have quantum computers yet that can run those applications. So why not? What is it that's taking so long? Well, it's really hard to make a quantum computer. And one of the difficulties is the phenomenon we call decoherence. Physicists like to imagine a quantum state of a cat which is simultaneously dead and alive. And we never observe in everyday experience that type of superposition of macroscopically distinguishable states of a system. And we understand the reason why not. It's because no real cat can be perfectly isolated from its surroundings. And the interactions with the environment, in effect, immediately measure the cat, projecting it onto a state which is either completely dead or completely alive. That's the phenomenon of decoherence. And decoherence helps us to understand why, even though quantum physics holds sway at the microscopic scale, still classical physics is quite adequate for describing most of the processes of our everyday experience. A quantum computer won't be otherwise much like a cat, but it too will be hard to perfectly isolate from its surroundings, and interactions with the environment can cause the quantum information stored in a quantum computer to be damaged, and that will cause the computation to fail. So if we're going to operate a large-scale quantum computer, we have to figure out how to protect it from the damaging effects of decoherence and other sources of error. Errors can be a problem even in the classical world. We all have bits that we cherish. But everywhere there are dragons lurking who take pleasure in damaging our bits, flipping their color. We've learned in the classical world some ways to protect our information. The important concept is that we can redundantly encode the information so that if it's partially damaged, we can still recover the information. So if I want to store a bit, which is one that I cherish, I can store backup copies of the bit, and then a dragon might come along from time to time and change the color of one of the balls. But I can also ask a busy beaver to frequently check the balls, and whenever she sees that one's a different color from the other two, she repaints it so all three match again. So unless the dragon has had a chance to damage 2 out of the 3 balls, the information is well protected because of the redundant storage. And we'd like to use the same idea that redundancy provides protection for quantum states. But at first there seem to be difficulties because, as already discussed, we can't copy unknown quantum states. So I can't, for example, make a backup copy of the state of a quantum computer in the middle of a computation in case my original gets damaged. And furthermore, with the quantum computer, there are more things that can go wrong with the information. It might be that a dragon opens door number 1 of the box and flips the color of the ball and then recloses the box. That would be like a bit flip that occurs for classical information. But instead, the dragon could open door number 2 and change the color of the ball and reclose the box. That's what we call a phase error on a qubit, and it really has no classical analog. We need to be able to protect against both the bit flips and the phase errors to make sure our quantum information is undamaged. There's another way of thinking about these phase errors, which is we might imagine that the dragon opens door number 1 and instead of flipping the color of the ball, just observes the color and remembers it. And that'll have the effect of changing the color as observed through door number 2. And in many physical settings, it's easier for the environment to remember the state of a qubit than to flip the qubit, and that makes phase errors particularly pervasive in some physical settings. So the key thing is that if you look at quantum information, you disturb it. And so if we want to protect quantum information, we have to keep it almost perfectly isolated from the environment. So there's no leakage of information about the state of our quantum computer to the outside world. And that sounds impossible because our hardware will never be perfect. So how can we perfectly isolate the quantum computer from the outside? But we learned in principle how to do it through the concept we call quantum error correction. And the essential trick is to use entanglement to protect the information. So if I have one qubit that I want to protect, I can encode that one qubit of information in an entangled state of 5 qubits, which is chosen in such a way that if the dragon comes along and observes or performs any action on one of the 5 boxes, that dragon doesn't acquire any information about what the encoded state is. Because the information doesn't reside in that individual box, it's a collective property of the 5 qubits. It's just like that 100-page book. When you look at one of the qubits at a time, the information is completely hidden. And so it's possible then to ask the beaver, after the dragon has acted on one of the boxes, to make some collective observations of the 5 qubits and restore the right kind of the entanglement. And in the process, the beaver doesn't learn anything either about the protected encoded state, and so that state can be undamaged. So the basic idea of quantum error correction is that we can use redundancy to protect quantum states, but we have to do it the right way. And the right way to do it is to encode the information in the form of entanglement among many parts of the system. So just like that 100-page book, which reveals no information when you look at one page at a time, the environment will interact locally with the parts of the system one page at a time, and in doing so won't be able to detect the encoded information or damage it. And we've also learned how to process information which is encoded in this entangled form, and so operate a robust quantum computer, at least in principle. So although we may never see a real cat in a superposition of the dead and alive state, we should be able to prepare an encoded state of a cat and maintain it in that delicate superposition state for as long as we please. When we understood these principles of quantum error correction about 20 years ago, we were very excited. And so my then student, Daniel Gottesman, wrote a sonnet. And I'll just read the beginning of it. We cannot clone perforce, instead we split coherence to protect it from that wrong that would destroy our valued quantum bit and make our computation take too long, and so on. Well, the point is, we were excited because we had understood that, at least in principle, we can make a quantum computer resistant to the effects of noise and decoherence. Now, another hero of this story is my CalTech colleague, Alexei Kitaev. The day when we met, which was about 20 years ago, was one of the most exciting days of my scientific life. When I heard his seminar and took these notes, I felt that I was hearing from Kitaev ideas about quantum error correction which are potentially transformative. And what I learned from him was the connection between quantum error correction and topology. Topology means the properties of a mathematical object which remain invariant when we smoothly deform the object without ripping or tearing it. And when we think of operating a robust quantum computer, what we want is for the protected information that's being processed to remain invariant even as we deform the computer by introducing some noise. So we would like to use interactions which take advantage of topological principles for the purpose of information processing. And physicists know of such topological interactions. For example, the Aharonov-Bohm effect. I can imagine transporting a charged particle like an electron around a magnetic flux tube, and then the quantum state of that electron is modified in a way that depends on the magnetic flux which is enclosed in the tube, even though the electron never directly visits the region where the magnetic field is non-zero. And that change, that interaction, is a topological property. If we deform the trajectory of the electron, the effect of circling the flux tube doesn't change. The only thing that matters is a topological property, the winding number of the electron around the flux tube. Now, if we can engineer two-dimensional systems, for example, in a layer separating two slabs of semiconductor, then there's a very rich family of possible topological interactions that can be realized. In these systems, if properly designed, we can have what we call anyons. And anyons have the interesting property that if I have a system of many of these particles, that the quantum information carried by the particles can be very complex, but when we visit the particles one at a time, that information is completely invisible, because it's not a property of the individual particles, but a collective property of all the particles. And that's just the type of encoding of information that we want to protect against noise. That information will be well hidden from the influence of the environment. And furthermore, we can process the information by performing exchanges of the particles in which they swap places. So we can imagine operating a topological quantum computer, which we would initialize by, in some two-dimensional medium, preparing pairs of anyons, then processing the state of those anyons by successively exchanging pairs of particles so that their world lines in 2 + 1 dimensional space-time trace out a braid. And then we could read out a final result, say, by bringing the particles together in pairs and observing whether the pairs of particles annihilate and disappear or not. So what's beautiful about this idea is that in principle we can do any computation we want this way, and the computation is intrinsically resistant to decoherence if we keep the temperature low so we have no unwanted anyons diffusing around, and if we keep the particles far apart from one another except at the very beginning and the very end so there's no unwanted exchange of charges between the particles, then as long as the world lines execute the right braid, then we'll do the right computation and get the right answer. So I really like this idea, which led me to write a poem about it. And I won't read you the whole thing, but part of it reads this way. Alexei exhibits a knack for persuading that someday we'll crunch quantum data by braiding, with quantum states hidden where no one can see, protected from damage through topology. Enyon, where do you roam? Braid for a while before you go home. And there's more to it than that, but the point is, it's a really beautiful, exciting idea. But it's a theorist's dream, and is it something that we can really realize in hardware that can be built? Well, here too, Kitaev had a seminal idea, which is to use the principle that under the right circumstances, we can divide an electron in half. Now, it sounds ridiculous because we know an electron is a fundamental elementary particle and it's indivisible. But in a highly entangled environment, in the right kind of two-dimensional medium, electrons can split into pieces, and anyons can arise that way. Well, here's one relatively simple setting in which that can happen, actually. In a one-dimensional wire, it's possible for the wire to be superconducting. That means it conducts electricity without any resistance. And there are two types of superconductor, what we might call the conventional type and a more exotic type called the topological superconductor. And at the boundary between the two types, there resides an object that we call a Majorana fermion. And now it's possible to add a single electron to this finite segment of topological superconductor, and that electron will, in effect, dissolve and disappear, so we can't tell whether it's been added or not. But in the process, the state of these two Majorana fermions at the two endpoints of the segment will have changed. But that change in the state of the Majorana fermions is not locally visible. We can't see it if we visit the endpoints of the segment one at a time. It's a collective property of the two. So that's the type of non-local encoding of information that we want to protect against errors in a quantum system. And this type of Majorana fermion in a superconducting wire, well, we have some very interesting evidence that it can be realized experimentally, but more experiments will be needed to make that case completely ironclad. Of course, we'd like to be able to do more than just store information reliably. We'd like to be able to process it. And using quantum wires, one way to do that would be to build a network of wires so that if I had two Majorana fermions, I would be able to change their positions, let's say with voltage gates underneath the sample, so that one Majorana fermion could be parked around the corner, the other move from right to left, and then the first one unparked. And that would perform an exchange of the positions of the two particles, which would be a kind of quantum operation, one step in a quantum computation which is protected from decoherence. That type of experiment hasn't been attempted yet, but I expect it will be in the next couple of years. And when done successfully, that will not just be an interesting step towards a future technology, but a real milestone in basic physics. Now, I don't want to give the impression that this exotic topological approach is the only way that we can build large-scale quantum computers. No, that's not at all the case. There are a number of ways of building quantum hardware which are currently being developed and are making impressive progress. I already mentioned one way of encoding a qubit using the polarization state of a single photon. There are a number of other ways. One is we could store our qubit in the state of a single atom, which could be, say, in either its internal ground state or some long-lived metastable state corresponding to the two states of a qubit. Or we could encode a qubit in a single electron, which has a magnetic moment or spin, which could be oriented either up or down. So these are two remarkable encodings, because in each case, we're encoding the information which is to be processed in a truly microscopic system, either a single atom or a single electron. Another possibility, though, is to use superconducting circuits, not the exotic topological type that I just mentioned a minute ago, but conventional superconductors, where, although in practice there are better ways of doing things, you could imagine encoding a qubit by choosing a state in which the current in a circuit either circulates clockwise or counterclockwise. That's a remarkable encoding, too, because in this case, the qubit involves the collective motion of billions of electrons, and yet for information processing purposes, it behaves like a single atom or electron and can be quite well controlled. We're not far away. I expect in the next couple of years we will have quantum computers with more than 50 qubits. And these will be systems which are sufficiently complex that we can't simulate them with digital computers that exist today. So this will be the onset of the age of quantum supremacy, in which quantum systems are performing tasks that go beyond what we can achieve in the classical world. And I think we should view that as the opening of a new frontier in the physical sciences, what we could call the complexity frontier or entanglement frontier. This is different from the frontier we explore in particle physics at short distances or in cosmology at long distances, but like those, very fundamental and exciting. And like those, in order to make advances, we need more and more powerful instruments. We are now in the process of developing and perfecting the ability to prepare and precisely control highly entangled states of many particles, which go beyond what we can simulate. We don't have the theoretical tools to predict very well the behavior of these systems, and that's going to open new opportunities for discovery. What are the things that we'll be able to do with a quantum computer, which we hope we'll have in a couple of years, with 50 to 100 qubits? Well, maybe one of the most important things is we'll use these smaller quantum computers to learn how to make better big quantum computers, in particular by testing and perfecting our procedures for doing quantum error correction. But we'll also be able to run at relatively small scales new kinds of algorithms which will already surpass what we can do with digital computers, study certain quantum simulation problems, for example, to investigate quantum chaos in new ways, or to simulate complex molecules going beyond what we can do classically. But once we have quantum computers that we can try out and play around with, I expect we'll discover a number of new applications which we haven't anticipated. Now, how far off is it that we'll have scalable quantum computers that can, for example, break the RSA public key crypto system, well, that's farther away, perhaps decades. You know, I said earlier that you can't solve this problem using digital computers, but that's not strictly true. It's just a question of resources. So if you wanted to break RSA as it's typically used today, it's possible, but you would have to cover about a quarter of the land area of North America with a server farm, and then you'd be able to solve the problem in about 10 years. But the catch is that with existing computing technology, the power consumption would burn up the world's supply of fossil fuels in just one day. So from that perspective, the quantum computer looks pretty good. If we just took the technology we have today and sort of brute force scaled it up, it's not quite as simple as it sounds. But suppose we did that, and this estimate was done by John Martinez, who's an experimentalist who works on superconducting qubits. Well, in order to have sufficient redundancy to do error correction, we'd probably need about 10 million physical qubits, and then we'd be able to run the algorithm that factors a number and breaks RSA in less than a day. And the power we would need is just 10 megawatts. The thing is, at the current cost of making a very good qubit, it would cost tens of billions of dollars. So the cost is going to have to come down, and it will. So there are three questions about quantum computers that I've been emphasizing. One is, what will we do with quantum computers? Why build one? And I think the best answer we have to that is that with a quantum computer, we'd be able to simulate, we think, any process that occurs in nature, which we can't do with digital computers, which are unable to simulate highly entangled systems. Can we really build one? Well, we know of no insurmountable obstacles to doing so now that we understand the principles of quantum error correction. And how will we do it? Well, as I've emphasized, there are a number of approaches to building quantum hardware that are under development and making good progress. And it's important to continue those different paths because different quantum technologies may find different applications, and we don't really know which technology will ultimately have the best prospects for scalability to large devices. But what I really find interesting is the ways in which our ideas about quantum computing are giving us new approaches to some of the other fundamental problems in physics, particularly quantum condensed matter physics and also elementary particle physics. There's been a surge of interest in recent years among the community of people who work on quantum field theory and quantum gravity in quantum information concepts. These people feel that quantum information ideas are highly relevant and useful for addressing the problems that they're interested in. And in a way, that's not so surprising, because the quantum gravity community has been struggling for 40 years with a very deep puzzle whose origin really has to do with quantum entanglement, specifically the quantum entanglement between the inside and the outside of a black hole. A black hole is a wonderful object, and one of the seminal papers on the subject, by the way, was by J. Robert Oppenheimer. It's an extremely simple object. It's composed of nothing but warped space-time geometry. Its defining property is its event horizon. If you are foolish enough to cross the event horizon and enter a black hole, you'll be unable to return to the outside or even communicate with your friend who stays outside. But the inside and the outside of a black hole can be and will be entangled with one another, and Stephen Hawking understood in the 1970s that as a result, a black hole will emit radiation due to quantum effects, and eventually radiate away all its mass and disappears. And that creates a puzzle because we can ask about what happened to any information that fell into a black hole during its lifetime. It's a foundational principle of quantum mechanics that information is not destroyed, though it can be scrambled up into a form that's exceedingly hard to read. So we're faced with an unpleasant choice. If we lose information inside a black hole and then the black hole disappears, that information is lost from the universe forever, then we have to recast the foundations of quantum theory. On the other hand, if that information manages to escape from the interior of the black hole, that means we have to rethink the foundations of general relativity. And after 40 years, we still don't have a clear and completely satisfactory resolution of this puzzle. What we can say about it, the best thing we can say about it, is that we've understood the resolution to a large degree, but not completely, in a particular setting, what we call ADS-CFT duality. And this is a description of quantum gravity in the case where the vacuum energy is negative and the curvature of space-time is negative. And in that setting, we have two complementary ways of describing the same physics. In a way, this correspondence allows us to put a black hole inside a tin can. The walls of the can are what we call CFT for conformal field theory, and that's just an ordinary quantum theory without gravity. And in the interior, we have gravitation, geometry, and quantum fluctuations of geometry. And a process in which a black hole forms and evaporates completely has a complementary description in terms of just the field theory on the boundary. And on the boundary, there's no black hole, there's no gravity, there's no place for information to hide, and so it seems manifest that the process can be described without any loss of information. So at least in this case, the one where we understand quantum gravity the best, it seems clear that a black hole does not destroy quantum information. But even so, we're left without a satisfactory understanding of how the information manages to escape. And in fact, it's not so clear how this boundary description encodes the experience of someone who falls through the black hole event horizon and enters the black hole interior. So to make further progress, we should try to deepen our understanding of this correspondence, which is the subject of much ongoing work. So let me say a little bit more about that. Here, for ease of visualization, I've indicated the boundary as one-dimensional, a circle, and the bulk geometry as two spatial dimensions. So here in this cut through the bulk, in order to indicate the negative curvature, I've used the Poincare disk description. Each one of these colored regions actually has the same geometrical size, but they appear to be smaller and smaller as we get closer to the boundary in order to capture the negative curvature. And the idea of the correspondence is that there are two exactly equivalent descriptions of the same physics, one on the boundary and one in the bulk. And there's a very complex dictionary, which is only partially understood, which maps the states and observables of the bulk theory to the corresponding states and observables of the boundary theory. But what has become increasingly clear in the last few years is that this geometry in the bulk can be viewed as an emergent property of the quantum entanglement on the boundary. What evidence do we have pointing in that direction? I'll tell you a few things that indicate that geometry can be thought of as emergent from entanglement. Well, one is what we call holographic entanglement entropy, which was discovered 10 years ago now by Ryu and Takeyanagi. So they asked the following question: suppose we consider some state defined on the boundary, and we're interested in a connected region on the boundary, and we'd like to know how entangled that region is with the complementary region. And they pointed out that there's an answer to this question which is geometrical in the bulk. We can quantify entanglement using entropy, which is a measure of how much information is missing from this region A, because it's encoded in the form of entanglement with the complementary region. And that entropy can be expressed in suitable units as the area of the minimal surface in the bulk which separates boundary region A from the complementary region on the boundary. And those units in which we express the area are just the same units that we use to express the entropy of a black hole in terms of the area of its event horizon. So we can think of where these minimal surfaces lie, which encodes the geometry of the bulk, as corresponding to properties of the entanglement on the boundary. So here's another example. We can imagine a boundary theory which has some holographic dual, has some higher dimensional gravitational interpretation, and we can consider two such theories and ask what happens when we entangle those two systems with one another. And the answer is that the bulk geometry corresponding to that pair of systems will have a wormhole which connects together the two asymptotic regions on the left and the right. And when there's no entanglement between the two systems, then there will be no wormhole connecting them. So this relationship between connectedness of space and entanglement was elevated by Maldacena and Susskind a few years ago to a general principle which they ingeniously called ER equals EPR. EPR means Einstein, Podolsky, and Rosen, who first discussed quantum entanglement in that 1935 paper I mentioned. And ER refers to Einstein and Rosen, who in that same year wrote the first paper discussing wormholes in general relativity. Now, if you had a quantum computer or by some other means you tried to remove the entanglement between distant regions of space, the effect of that, according to this ER equals EPR principle, would be that the space would break up into fragments. So there's a sense in which entanglement provides the glue that holds space together. Now, this wormhole can't be used to travel quickly from one region of space to another. It's not a traversable wormhole. This corresponds to the property of quantum entanglement, that we can't use entanglement to send an instantaneous message from one party to another. What happens is the wormhole is dynamical. It grows too quickly for anyone to pass from one end to the other. So you might think, if a wormhole isn't traversable, that's not really very much fun. But actually, it's a lot of fun. Because we can imagine two lovers, Alice and Bob, who live in different galaxies and long for each other's company, but it's completely impractical to travel from one galaxy to another. But let's say Alice and Bob had the foresight to prepare many entangled pairs of particles, and Alice took one member of each pair and Bob took the other member of each pair. Then Alice could take her particles and gravitationally collapse them to make a black hole, and Bob could do the same. And those two black holes would be entangled with one another, and that means they would be connected by a wormhole. Now, Alice wouldn't be able to jump into her black hole and emerge from Bob's, but Alice and Bob could both jump into their black holes, and then they'd be able to meet inside the wormhole and have a fulfilling relationship for a while, but ultimately they'd be destined to arrive at the singularity inside the black hole and be torn asunder. So it turns out to be a tragic love story. Now, another thing that's become apparent in just the last couple of years is that there's a connection between this dictionary, between the Vulcan boundary theory and quantum error correction. That if I consider some local operator deep inside the bulk geometry, the corresponding operator on the boundary is a very non-local operator. It's just the kind of mapping from local to non-local that we need to protect quantum information from damage, just the kind that occurs in a quantum error-correcting code. And so the bulk geometry deep in the bulk is actually very robustly encoded so that if some damage occurs on the boundary, that bulk geometry won't be much affected. So I'm hopeful that this insight can be taken further. It's really a remarkable illustration of the unity of physics. We developed the idea of quantum error correction because we wanted to keep quantum computers from crashing, and we wound up with a different perspective on the geometry of quantum spacetime. So far, we've understood this within the context of this, or partially understood it within the context of this ADS-CFT duality. But we'd like to broaden our understanding beyond the context of anti-de Sitter space, because anti-de Sitter space isn't the real case that we want to solve. Anti-de Sitter space, the thing that we understand reasonably well, that's the case where the vacuum energy is negative and the curvature of space-time is negative, but it just so happens that we live in a universe where vacuum energy is positive and curvature is positive, what we call de Sitter space. It's much easier to do quantum mechanics in anti-de Sitter space because there's a boundary. And we can make reference to the boundary when we want to discuss the observables of the theory. De Sitter space doesn't have a boundary, and that makes it much harder to understand quantum physics in that setting. But we're going to have to learn how to do quantum mechanics in de Sitter space because that's where we live. And I'm confident we'll figure it out eventually, but it's hard. Last year, Robert Digraph, the director of the Institute for Advanced Study, spoke at a CalTech event, and he showed this slide near the end of his talk, and I was quite struck by it because he was trying to illustrate how the different ideas of theoretical physics are connected, and he put quantum information right in the center of things. I don't think he would have done that a few years earlier. This idea that quantum information is a unifying principle of physics has really only started to take hold in the last couple of years. But unlike Digraph, I would cross out the word theoretical because quantum information is an experimental subject. And if it's true, as we increasingly have reason to believe, that we can think of the geometry of space-time as an emergent property of quantum entanglement in some underlying system, then we should be able to get insights into quantum gravity by doing laboratory experiments. So I anticipate that in the coming decades, we will gain deep insights into the quantum structure of space-time by doing laboratory experiments with highly entangled quantum systems. That on a tabletop in a laboratory at a place like Berkeley, we'll be able to, in effect, to create space-times that didn't exist before and explore their properties and learn new things. Well, whether that prediction comes to pass or not, I think we can be highly confident that we'll find many surprises and discoveries as we explore the entanglement frontier. Thanks a lot for listening.
Thank you, Professor Preskill. We normally allow a few minutes for questions at the end of Oppenheimer lectures, and we try to have a mix of questions from both professional physicists and amateur physicists. And if you managed to follow the talk, then you're already an amateur physicist at least. So please, any sort of question.
How do you feel now about the bet you made with Stephen Hawking in 1997?
Now, the question was about a bet. This will be the opening line of my obituary, I'm afraid. I won a couple of bets with Stephen Hawking. And in particular, one of those bets concerned the question of information and whether it can escape from black holes or gets permanently destroyed. Hawking and also our friend Kip Thorne took the position that black holes destroy information, and my side of the bet was that black holes actually just scramble up information into a form that's hard to read. And Stephen has recanted, but he believed very deeply at the time that black holes destroy information. And it was a bit of a shock to me when he conceded this bet in 2004. It was a rather dramatic occasion. We were at a conference in Ireland in a big convention hall in Dublin, and somehow the word had leaked out that Stephen was going to make a big announcement. And so there were 100 people from the press and various amateur physicists. Michael Flatley, the Lord of the Dance, it turns out general relativity is his hobby. He was there. And so Stephen gave a technical talk, and then at the end, he presented me with my prize, which was a baseball encyclopedia from which you can withdraw information. He knows I'm a baseball fan. This was very hard to get in Ireland because you can't get a baseball encyclopedia in Dublin, so we had to have it shipped overnight. How do I feel about it? Well, I was surprised that he conceded because I think we still don't have a satisfactory understanding of the problem, and he would have been well within his rights if he had decided to hold out longer until the question is definitively settled. I mean, I still think I took the right position, and now Stephen agrees with that. Kip does not. He has not conceded. But I don't think we really have a 100% convincing argument that information escapes from black holes even today.
Thank you.
Can you tell me, can you describe the hardware? Can you describe? Oh, thank you. Can you describe the hardware that will replace the transistor chip in the quantum computer? In other words, I'm interested in what the hardware is going to look like.
So the question is, what will the hardware look like in a quantum computer? Well, I mean, we have quantum computers now, but they're small. And so I think you're really asking about the scalable quantum computers of the future, where we might have millions of physical qubits. So the honest answer is I don't know exactly what the hardware is going to look like. But actually, here at Berkeley, in the Siddiqui group, they're doing terrific work on quantum computing hardware with superconducting circuits, and they can show you a device that has 10 qubits in it, which is based on superconducting technology. We can imagine scaling up devices like that to millions of physical qubits, though it's going to be very challenging. Another approach, which in the long run I think has a lot of promise, is using, as I mentioned, electron spins as qubits. That technology is lagging behind at this stage, but it's something that is perhaps especially compatible with the silicon classical technology that we have now. And I also mentioned these topological approaches where it's even less clear what the hardware is going to look like, but I gave sort of a cartoon version of it in my drawing of a quantum wire. Mm-hmm.
You mentioned you expect that a lot of these questions will be answered by experimentation, experimental physics. What kind of experimentation? What does that look like? Or is it the same answer as the last question?
Well, so what I had in mind is that we have understood to some degree that it's possible for a quantum system which doesn't involve gravitation at all to behave like a system that has gravity. And that's what this story of the ADS-CFT correspondence is about. So the example we've been able to understand is a very special one. It has lots of symmetry. It has special features. But I think the phenomenon of a highly entangled system behaving like a gravitational system is a more general one. But we don't have the mathematical tools to understand it in other contexts. So what we'll need to be able to do experimentally, I think, is build systems in which there are many particles which all interact with one another in a typical system that's easier to realize. The strength of the interactions between the particles depends on how distantly separated they are, and it falls off with distance. But I think the kind of system that we would need is one with many particles or degrees of freedom, which all have strong interactions with one another. And in such systems, then we'd be able to drive them and make measurements of the way the different parts of the system are correlated with one another. And the task would be then to see if those correlations have an interpretation in terms of some kind of gravitational system.
So
we can't really understand quantum entangled states. So we would have a computer, and we would take classical information, put it into a quantum computer, wait a while, and take a classical solution out that we can understand. And just curious how you get it in and out, and I guess the contradiction between the number of states inside the computer versus the very simple states that we can comprehend, put it in and take it out.
Right, so the question is, how do we get information into and out of a quantum computer? As the question anticipated, the information that we put in and we take out is classical. The processing that occurs can't be done classically, but is done in a quantum device. And it's the task of the designer of quantum algorithms to understand how to do that quantum processing. But the initialization and the reading out are easier to describe. So if I have many qubits, I mean, in my cartoon analogy, the preparation would just consist of putting a lot of balls in door number 1 of a lot of qubits, and then a lot of quantum processing goes on, which can't be described classically, and in the end, we open all the boxes one at a time. So the preparation would just be preparation of 1 qubit at a time, like, let's say it's a bunch of electron spins, and we prepare them so that they're all pointing spin up, and then we do the quantum processing, and at the end, we just observe the spins one at a time and see whether they're pointing up or down. Or in my analogy, open the box to see if the ball is red or green. So the process of initializing and reading out is not so exotic. The art of designing a quantum algorithm is to figure out how to make use of the quantum entanglement at intermediate stages to speed up the solution to a suitable problem.
Is there a chance that quantum computing will extend the validity of Moore's law into a longer span of time?
So the question was about Moore's law and whether quantum computing will extend Moore's law further into the future. Of course, Moore's law is the miracle that we've all been living in for 50 years or so. We've seen exponential improvement in the performance of integrated circuits, although we've reached the stage now where it's getting harder and harder to increase the clock speed, and a lot of the improvement is coming from increasing parallelism of classical systems. And it's an amazing story, and I think a very instructive one for quantum technology. If you go back to the 1960s when Moore and others were thinking about the prospects for improving integrated circuits in the future, they couldn't imagine things like an iPhone. It was just far beyond what the technology was pointing to at the time. And in the case of quantum technology, I think we're in a similar situation. We are now starting to interact with information in a completely different way from anything that happened before. And we don't know where that's going to take us. We have a few ideas of how we will apply quantum computers. Undoubtedly, we haven't thought of the most important applications that are going to arise in the future. So I think my answer to the question is that we've seen in recent history, and even longer-term history, that physics can drive the economic expansion of the world, that the technologies that come out of physics eventually have a big, big impact on the way we live our lives. And we've certainly seen that with the basic physics in the 20th century of understanding semiconductors, which led to integrated circuits, quantum physics of lasers, which we make use of in many ways today. But that 20th century physics, that was the physics of, if you like, single particle quantum mechanics. And now we're getting a grasp on a new quantum revolution, the properties of many particles, and I think that could well drive economic development in the 21st century. But nobody really knows, and so I don't have a precise prediction about the quantum Moore's law. But I think we can expect that these new technologies are going to take us to remarkable places that we haven't yet imagined.
In quantum mechanics, electrons are indistinguishable. Are qubits also indistinguishable?
So the question was about indistinguishable particles, that we know that electrons, for example, are indistinguishable, and does that apply to qubits as well? It need not. I mean, it's possible for the qubits to be distinguishable. For example, in these superconducting circuit realizations of a qubit, each qubit is actually an engineered device. They're not all identical. And so there's no notion of indistinguishability among the qubits. That doesn't impair the quantum computer's ability to perform its special magic. In the case of the anyons I described, they can be viewed as a rather exotic type of indistinguishable particle. And that's why it makes sense to process the information by exchanging the particles. That affects the information that's encoded in the many-particle system. But when the anyons change places, when you look at them one at a time, they all look the same.
Do you subscribe to any particular interpretation of quantum mechanics?
The question is, it's a question for me personally, do I subscribe to any particular interpretation of quantum mechanics? I'm an Everettian. I like the idea. Sometimes people call it the many worlds interpretation, though I'm not very fond of that name. But I think the essence of that point of view is that there's really just one way for things to change in the world. Technically, quantum states can change by evolving in a way which doesn't create or destroy information, that is unitary evolution. And that's the only thing that ever happens. That measurement is not a fundamentally different process. Now, this is a subject that people can get emotional about. Disadvantage, you might say, of that point of view is that in order to understand why when I observe a quantum system I see one definite outcome, I have to include myself in the description, because what really happens is that there's more than one possible outcome, and I become correlated with the state of the system I'm observing. And some people think this is a very extravagant thing, that we have to keep track of all the possible outcomes by including the observer in the system. But I prefer that to introducing measurement as some kind of new fundamental process. However, I think, everybody's entitled to a certain degree to their own interpretation of quantum mechanics that they prefer. Different interpretations can give rise to different insights and can help to generate different ideas. I mean, I think to me, the question of interpretation is most interesting to the degree that it raises questions about what the alternative to quantum mechanics might be. Maybe quantum mechanics will fail, and some people expect quantum mechanics to break down at some stage because of the issues of interpretation. I'm not sure whether that's true. But I think thinking about interpretations can be useful, particularly if it suggests new ways in which we can test quantum theory and look for deviations from it.
Maybe one last question in the back.
The question that I have is, technology is highly dependent on materials. Have you thought about promising materials that could be used for these quantum computers?
So I think the question was, well, technology is very dependent on advances in materials, and what can we say about how advances in materials will impact quantum technology? Was that more or less the question?
What type of materials might you use in quantum computers?
Yeah, well, there are materials issues in all of the things that I mentioned. There have been tremendous improvements, for example, in the performance of superconducting qubits going back 15 years, and many of those improvements have to do with using superior materials to make the Josephson junctions, which are the essential ingredient in the superconducting circuits that makes them controllable and behave quantumly. These topological quantum computing ideas, computing with anyons, that's very much a materials issue. It's been a great challenge to synthesize materials and to fabricate devices that bring together all the physical ingredients that we need to make topological quantum computing work better. Spins in semiconductors, same thing, that materials issues are currently a huge impediment, and improvements in materials will surely lead to improved technology.
I think with that, we should call it a night. Before we go, let's thank Professor Preskill for a beautiful and stimulating Oppenheimer lecture.